Today, we'd like to have short 5-10 minute topics. We had a few volunteers already, and we definitely have room for a 5 or 10 minute talk about something that's of interest to you in the science realm. So that's coming up. I've got on the tall table in the back there, I've got the science sign-up sheet. 4 S's, Science Slam sign-up sheet, yeah. So put your name in a way for me to get in contact with you on it, email or phone number or something like that. And if you've been to some of the science slams before, they've been a lot of fun. People bring up topics. We have a physics teacher that has done demonstrations before of different things, and Scott and I have talked about stuff, and people come up with all sorts of different topics. So we'd love to have you. It's a fun way to kind of end the year. We generally don't meet through the summer. The church is on a kind of a hiatus. There's lay-led meetings and so on. The minister in the Unitarian Church gets the summer off, so that's kind of nice. And so Scott and I have generally taken the summer off to recharge and do some stuff as well too. But is this loud enough? Can you hear me all right? Okay, good. Great. All right. Welcome to Science Sunday, May 2024. I really recommend getting this book by Dava Sobel, if you have an opportunity, called Longitude. And she tells a lot of the stories that, and more, many more, and in much more detail than I'll tell today. But it's interesting. We don't really think about it much. In fact, if you have your phone available, you can go any place you're at, and you can just type in www.latlong.net. And it'll tell you, you can go to a map and put down where you are. It'll tell you the exact latitude and longitude to something like 6 or 7 decimal places. So do you think you have the same latitude and longitude as Dave does in the back of the room, Scott? That's the amazing accuracy of what we can do now. We can tell where we're at anywhere in the world to something like 7 decimal places of accuracy. And that's all based on our knowledge and our capacities now. So people that go traveling, as long as they got a charger to keep their phone going or some other way, they're in pretty good shape. But longitude was, like I said in the blurb that talked about today's meeting, the biggest scientific bugaboo, the biggest challenge of the 18th century and 1700s and before that as well too. Generally, people that traveled, well, let me just going in, there it is. So this is our latitude and longitude with an extra E put it in there, I just noticed, the DuPage UU Church. But you can go to www.latlong.net and you'll find something very close. This room is very close to these numbers, okay? 41.804014 north latitude, north of the equator, and longitude of 88.118076 west. If you have a phone and want to do it there, you can see how close you are to that as well too. Okay, so you can use those numbers and calculate exactly where you are on the planet and where you are on a map, and it's all very easy and comfortable for people right now. But it always wasn't simple like this. Okay, you may have heard about the Isle of Scilly off of England, and the Scilly naval disaster of 1707, which got Admiral Sir Cloudesley Shovel in the history books. He had just taken a fleet of somewhere around 15 ships from England down to the Straits of Gibraltar, handily defeated the French fleet, won a great naval battery, and then sailed back to England. Okay? On his way back, you can see on the, Joanne, you know how this thing, do you know how this thing? No, I don't want to go back, I want to indicate the point. Okay. Thank you. So here's his trip back. Science. His trip back from the Straits of Gibraltar. This is his calculated position. They had terrible weather, storms, you can see in the wood cutting on the right, and they couldn't get accurate readings of where they were. So they didn't know exactly where they were. They thought their calculations said they were here, when actually they were here, and there's the Isle of Scilly, okay, headed for disaster. 5 ships sank, 2,000 sailors died. The admiral himself died. There's a legend that he swam to shore, the only one to escape from his ship, and then people on the Isle of Scilly had basically one job, which was to wait for boats to crash on their shores, and then they plundered the people and killed the survivors and so on. So the story is that a woman saw him gasping on the beach and killed him for the ring that he had on his hand, and told that as she was dying many years later, told the story. So how can it be that you can't tell where you are and how you're in these positions? And especially getting into this narrow channel, you know, the capacity for danger, the capacity for problems to occur in this was just monstrous. You were hoping for, you know, proper direction and proper insight. So 1707 was kind of a culmination. There were many stories before and after this of terrible disasters at sea. Basically, sailors knew one of their means of getting around. They knew latitude very easily. Latitude was very easy to define. If you want to think about how you can define latitude, it's very sure that the sun comes up because of the tilt of the earth and the rotation of the earth and so on. As the height of the sun comes up at the highest point of the sun, then you know that that's different depending upon where you are on the globe, right? So if you're here, the sun would make a very small shadow. You could put just a stick, maybe a meter-high stick on your deck of your ship, and you could see the shadow that it makes, right? And for example, that's how Columbus got across, and most explorers got across the Atlantic Ocean in those days. They would check the highest, the shortest length that was created when the sun was at its highest. It would create the shortest shadow, and they'd see that this shadow was, 42 inches long or 17 inches long, whatever the shadow was when it was at its shortest, which meant the sun was at its highest. And then they could go and travel on another day, and then they could take another reading at midday, and they could see, well, the shadow's a little bit shorter here. That means I'm a little bit further south, and then they could redirect to compensate for that, okay? If the shadow got longer, then they could compensate for that too. So that meant that sailors in those days, they sailed the parallels, they called them, the parallels of latitude. They found the best way to get across the ocean, and they followed that. The latitude was very easy to find and very easy to know. You could have charts. You knew that wherever you were, if you were 500 miles further east or further west, the sun was still going to, because of the tilt of the earth and the rotation of the earth around as it rotated, there would still be the same shadow created if you were at a certain latitude, okay? I kind of wanted to make this be a discussion. If it gets to be a point that people want to bring up a point about it or add some knowledge to it or something like that, feel free. I'd like to do that. Scott, you can probably hand around a microphone to make sure that we can do that. So latitude is very easy. The thing is, it's very predictable too. So not only did people going from the Bahamas back to England or different places like that, not only did they travel those parallels of latitude, but pirates and other people knew exactly the latitudes that they'd travel on. They knew the safe routes. You couldn't go off that route and change very easily as well too, because you were coming into other potential dangers. You didn't know that route so well. But if you stayed on that route, the pirates were waiting for you at some place too. Sometimes the pirates, the value of some of these Spanish ships that were coming back had more value than the entire income, the entire per capita income, or the entire income of England, right? One ship could have more value in it than the entire value of all of England's output in those days. Scott?
I was also going to talk about the latitudes have different weather patterns associated with them. So you've got the horse latitudes and the doldrums. Different kinds of weather patterns would be common in different latitudes. So it wasn't just about getting from here to there, it was also knowing what latitudes to avoid. Like you wanted to avoid the doldrums where there typically aren't any trade winds.
Right.
And so
Right.
that was a very important part of navigation as well.
Excellent, yeah, true. So, the Scilly naval disaster of 1707 kind of lit a fire under Parliament in England, and they decided in 1714, they had 7 years of debate and discussion, to decide to put together the Longitude Act. Go ahead, Scott. Right here, second row. We're going to keep you moving.
I like it. I need it.
No, just,
When were watches created that worked on ships?
ah,
As you mentioned noon.
uh-huh.
I didn't know when it was noon. Did they just watch the shadow until it was the greatest?
Well, noon is something that's pretty interesting topic. We think of noon, and watchers will tell you when 12 o'clock is, right? We meet at a certain time. We meet at 10:15. But if you'd have a sundial, in those days, sundials didn't always show. Sundials weren't accurate to the event that a watch could be, even. So a sundial doesn't have the accuracy. It comes in, it varies depending upon different fluctuations in the Earth's
Also,
time.
local noon is always when the sun is at its zenith.
Right, you can measure local noon. You can measure noon wherever you're at. It's when that shadow of that stick would be the shortest, right? That's noon. But when it's noon in the middle of the Atlantic Ocean, it definitely isn't noon anywhere else, back in London, England, or anywhere else, right?
No, the ship is moving, so.
Yeah, and the ship is moving, so
Right,
that makes
and-
it hard to keep time. you
Right,
say.
so time is hard to keep, but you can get some issues at it. All right, so the 1714 Parliament put out the Longitude Act. We'll talk about, why was it historically difficult to calculate longitude, okay? So if you think of the parallels of latitude, they're very even, they're set by the size of the Earth, and they're set by certain conditions of the Earth. Because the Earth is tilted, the farthest that you ever get, the sun at a certain position that's called the Tropics of Cancer and Tropic of Capricorn, above and below. When you never get sunlight for some of the year, that's where the the Arctic Circle and the Antarctic Circle are. So there's always things that are defining parallels. But nothing really defines longitudes except the fact that they're slices of the circle, that's the globe, that travel, all of them, through the North Pole and through the South Pole and back around the other side, right? So there's slices. Oh, okay.
It was Carl back there making those noises, wasn't it?
Go ahead.
Wait, let me get the mic to you. Otherwise, you won't be audible on the video we're streaming.
During this time, like the Polynesians were the foremost travelers. Did they use the same type of methods as the English?
They were very good, latitudes were pretty much endemic. You can count on parallels and going along a certain way, but they were very good readers of currents, as far as I know. I'm not highly versed on their skills, and I don't know if anyone really knows all the skills that they used, but they were masters of dead reckoning, knowing how the currents were flowing and how things were going, but I'm not sure exactly what they knew. It looks like
In
Joanne
answer to
knows.
that, there was a big thing on public television talking about the navigators, and because that's the word that we use for them. And they were very, very good at looking at the currents and the wave patterns. And as the sea passed over an island, it caused a refraction. Yeah, and you could see the interactions between them, and it took them years to become highly skilled, but they could tell you where land was and where it wasn't.
Right.
And so because the Pacific is just loaded with islands, they navigated from island to island until they got to Eastern Island, and then they ran out of islands.
Right. I'm sure they were masters of the star, the sky, and you know, the universe, looking at how things were. Again, in the northern hemisphere, you can find north by the Big Dipper and the Polaris star and so on. So they were masters at all that, things that we don't have to do because we can just pull things up on our watch and a map will tell us right where we are, right? So they had talents that we didn't really use, okay? But longitude has nothing that really marks it. There's nothing that happens easily seen on the Earth as compared to heights of a stick or something like that, heights of a shadow of a stick, that help show you latitude. There's nothing that really helps show longitude deeply about this. The longitude in some place, in one part, as you rotate around, as you go to new places, you'd see similar types of things there too. There were solutions that people were looking for, and we'll talk about some of them in a minute. But longitude is a challenging problem. Basically, when mariners got out in the ocean, once they lost sight of land, they were lost at sea. They used their best knowledge. They used dead reckoning. They threw big logs behind them with knots tied every distance, and they saw how fast the knots were leaving the boat, right, counting the knots, and then they were talking about how many knots they would go, and so they know the speed, but that can be affected by weather, by wind, by current, by a lot of different things. So dead reckoning got them so far, but wasn't perfect. There's stories of people trying to get around the bottom of South America and the terrible storms that go there. One story is a guy and his boat, he got separated from the others in his fleet. He went for something like 35 days heading straight west, and finally got to a point where, you know, and he didn't really know where he was. He got to a point where he thought, I must have missed the island I was looking for. He knew he was on the right latitude, but he didn't see this island yet. He turned around and went back for a number of days and realized that, no, this wasn't right again. And during this time, people on his boat, there were like 500 people on his boat to keep it running, were dying at the rate of 10 to 12 people a day from scurvy and just terrible, you know, malnutrition and things like that. He had to turn around. He finally figured out he was somewhere about 4 hours from getting to that island when he first turned around and went away. So a lot of tragedies and terrible, terrible things went on because they couldn't tell where they were, right? They couldn't verify where they were. So I wanted to talk about some of the historic methods that they used to try to determine longitude. And it was so critical, people came up with all sorts of possible solutions. One was magnetic compass dips. They knew that that they saw funny things happening. I have an orange here representing the globe, and I stuck a clove in here that you maybe can see, all right? And actually, this is at 23.5 degrees. This would represent the axis of the Earth, but true north was not in that same, at the same axis that the Earth spins on, right? So their theory was that if you're in a certain place, we can all look at it about the same, if you're in a certain place, true north and the spinning north line up pretty well, right? Magnetic north, and yeah. So those two line up pretty well, and you'd have a compass there. If you're in a different place on the globe, then you see there's a variation between true north, which Polaris would show you, right, and how the needle is pointing on your compass, right? So they had to correct for that, and they said, oh, I'm over here probably. It wasn't very accurate, and it wasn't very good. It was a try at something, right, knowing what they knew about science at the time. But actually, magnetic north moves yearly, moves all the time, right? So it was a very ineffective means of telling it. It gave them some level of thought. It probably told them if they were in the Atlantic or the Pacific Ocean is about what you could count on there. So it was something that they thought, as we develop better and better science, we'll be able to use this and do it. So there was an emphasis for a while, but it wasn't really good. 1676 was a lot of emphasis put on that. And they said, that's not working. We've got to come up with something better. So they came up with wounded dog theory. There was a story, there was a feeling that you could put on a powder of sympathy. And if a dog was injured and you put a powder of sympathy on the dog, it would bark and howl and so on because it was injured. And this powder of sympathy, they seemed to think it would happen at a certain time of day. Not only that, not only would that dog howl at the certain time of day, if you wounded it at noon, let's say in London, and then you put the dog on the ship, so you have to keep a wounded dog along with you on a boat and maybe continually re-wound it or something. It's getting a little bit.
It's time to poke the dog, Mike.
Yeah. Then, if you would be back, that dog would howl at a time when that powder of sympathy not only worked on that dog, it also worked on the implement that wounded the dog, is the theory. So you had an associate working back in London whose job was to run to all the different knives that wounded all the different dogs that were on all the different ships in the Atlantic Ocean and pour the powder on the knives that had wounded the dog. The dogs would all howl and everybody'd say, it's noon in London. They'd look at their clock and it wasn't noon where they were, right? But they could figure out where they were based on that.
Hi, my name is Lisa. I'm a guest here singing with the choir. But
Thanks.
I read, so, listening to this, it sounds very, very silly. I also read an article recently after dog sitting that dogs, many dogs, if you have dogs, oftentimes they go in a circle before they defecate. And I read an article that says that dogs actually align themselves north and south before they go to the bathroom. So maybe they were onto something but missed it just a little bit.
Right. We'll have to do some study on that.
My dog was a compass.
So you never know. It's worth looking into, right? Scientific things, you can find out the weirdest stuff sometimes, and this wasn't one of them. But so the wounded dog theory was actually after the magnetic compass dips, but they were still trying to look for solutions. Then they thought, a couple of mathematicians got together and thought, what if we get out and in the Atlantic Ocean and we start putting in, this is before they were really going into the Pacific, but they thought they could put out signal boats in the Atlantic Ocean that were tethered to the ground and they knew right where they were. And you could determine their spot, and maybe they'd be every 15 degrees of longitude. And 15 degrees is important because a circle is 360 degrees, and if you take 360 degrees and divide it by 24 hours in a day, that's 15, right? So every 15 degrees, the sun gets to noon 1 hour later, right? So if you find out that, your wounded dog howls at 9 in the morning, and it's noon in London, then you're 3 hours further away from London, right? But their thought was, let's have easy on the wounded dogs. If we station signal boats out there, and they thought they'd be anchored to the bottom because to them they thought the Atlantic was only about 200 fathoms deep, and that wasn't too bad to anchor to. But you could have these stationed, and every noon of London time, they would be on a time that they would shoot cannons and set up rockets and things like that. So anyone within miles of them could see and know what time it was, that it was noon in London right then. It had a lot of technical difficulties with that concept too. There's parts of the Atlantic Ocean that are, I think, 3,000 fathoms deep or something like that. So there wasn't really an effective means. Plus, can you imagine being light keepers, have enough of a problem, right, on land. Can you imagine being stationed on a boat, and being out there in the middle of somewhere, and how do you get your food? How do you have any entertainment? Maybe they'd have a whole bunch of books for you to read or something like that, but they didn't have science videos at the time, so Scott and I wouldn't have been happy with that. Yeah. So it never really took off, but it was a concept.
Oh, wait for the mic, please.
Did they really try it, you're asking? No, but there were two famous mathematicians who seemed like their heads were up in, thought land, and they thought that there were concepts. It's actually, when you think of it, yeah, it's a it's a workable theory, right? And they were expressing things. They put out popular missives about it. They were writing letters to the editor. They were doing a lot of things. They were presenting at Science Sunday talks in those days and talking about the value of doing it. But actually, it foresaw, it presaged, let's say, things that are ways of doing things nowadays. Before GPS, where now you can tell exactly where you are, there was a system called LORAN, right? And LORAN sent out signals from established places, and you could get 3 of those signals and triangulate between the 3 of them, and with a computer you could determine where you were pretty accurately. So, what's that? Right, yeah, the computations weren't computer. Well, LORAN, my brother was a pilot in Bering Sea, and they had computerized, yeah, for LORAN. But before that, I think you're right, that they did it with slide rule, calculate distances and lengths, and come out with the sweeping compasses that they always show you in the Mutiny on the Bounty movies and stuff like that, right? Yeah.
Did they have that during World War II to help with navigation, the radio beacons and stuff? I
I'm
don't
not
know.
positive. I would think they did. Do you know, George?
It was later than World War II?
Was it?
LORAN? Okay.
Okay.
Yeah, it was stations on land.
In the back.
Oh,
One could just say that the signal modes are the GPS satellites today.
yes, the comment was that GPS satellites or geostationary satellites that stay in the same place, the
Right.
same kind of idea.
Right, the satellites of today. And the satellite, we couldn't use GPS right now and be as accurate as we are without taking into account the theory of relativity and Einstein's work, over 100 years ago. It's amazing that actually plays
Hey,
into
that's my
things.
topic. You just stay away from that.
Dead reckoning, we talked about a little bit, just kind of your sense of where you were in the ocean, measuring how fast things went, but that was all affected by currents and storms and weather and different things like that too, and people were mistakenly, were surprised very often with their dead reckoning being as inaccurate as it came out to be. But it was a skill that gave them a good idea, and at times it worked well, and at times just the elements and confused them so much they were in trouble. Then we get to some scientific techniques. The lunar distance method. It's an interesting concept, and here's where, try to stay with me on it if you can. If you look up anywhere on the Earth, you'll see that the moon moves about the width of itself, the diameter of itself every hour. So the moon moves through the sky at a pretty regular pace. And there's stars that are way behind it and near it and so on. And that you can see the relative distance change, right? So a moon can go across a star. If you look at that and see, if you'd imagine, would it be a big difference if you were in London and you saw at nighttime, you saw that star being covered up by the moon? Would it be a much different point in time than if you were in the middle of the Atlantic and saw it?
The parallax for the angle of the moon, right? Mm-hmm. Yeah. I'm visual aid here, so that's the moon.
And what are you?
God.
Okay. That's in the next one. So actually, the answer is there is a difference, right? You'd see it pass at a different time. Okay. And so if you look at that, there could be charts made that would say, when does that pass and when does it hide? Actually, a lot of the charts were made in which it was the center of the moon and the point of the star, so you were looking at it going at that point. Of course, you didn't see the star when it was behind the moon, so you had to see it when it got to the perimeter of the moon, and then do some calculations from there, which they'd supply with charts. Depending upon where the moon is relative to the Earth in its orbit, sometimes the moon is slightly bigger because it's closer. Sometimes it appears slightly smaller. It isn't really bigger, it just appears bigger because it's closer. And when it's further away, it appears smaller. So those calculations had to be taken into it. So people were studying all these positions of stars. There was the first royal astronomer who was put in by King George II, I think. He spent something like 45 years just charting all the particular points of thousands of stars and the moon and all this to put in charts and to try to make predictions for the future. Because once it happened, all that data didn't mean that much anymore. It was only useful in making predictions for the future, right? So a whole bunch of calculations. His name was Flamsteed, and it's the Flamsteed Observatory at Greenwich now that was built for him to be in. And he spent something like 40 or more years of his life just studying positions of stars in the sky to do this, okay? So this whole lunar method had its strengths and weaknesses. There were so many variables involved. Like I was saying, the relative size of the moon, and then the variables of weather, right? How you can't take at certain times. The positions of the moon during the day. Half the time the moon isn't around at nighttime, right? Because of the pattern of the revolution of the moon. So it was something that could be done once in a while. It was also something that was a lot better done on land than at sea. Imagine being on a rocking ship, and you're trying to see, did that star go behind this thing or not, and trying to determine when that actually was pretty tough to do. But it could confirm certain things. It could confirm points at land when people like James Cook were traveling and making fantastic maps. He traveled for 5 years over the course of the Pacific Ocean and up to Alaska and so on, and he could get onto land and then recalibrate exactly where his longitude was. But he wasn't just a fantastic seaman, he was a fantastic navigator, right? And navigation was an important thing. One thing that was important, and maybe you've read it in the Rhymes of the Ancient Mariner, if you've read that poem, most navigators were talked about as being blind, generally blind in one eye, right? And you know why that was? They were taking sightings of the sun almost every day, and they're looking up with a special instrument, and then maybe they put a piece of smoked glass in front of it or anything like that. But basically, and they were laying down to get a good reading, and you wanted to be really accurate in your reading, so they'd take half an hour looking directly at the sun. And so it was kind of a mark. If you saw, in those days, if you saw somebody with a really, really strong right arm, they were a really good carpenter. Somebody who was blind in an eye was definitely a navigator. Or maybe a soldier.
Or a duelist, yeah.
Or a what?
Somebody dueling.
Oh, yeah, duelist, yeah. All right, so the lunar distance method, and a lot of these were very much loved by the intelligentsia of the time, the astronomers. There was a royal astronomer made. What kind of way is he going to like to measure where longitude is? He's going to like this lunar reckoning thing, and they spent, like I said, 40 years developing these things. Galileo actually knew about the problems, and he was the first to, with telescopes and aid of the telescopes, he was actually able to locate 4 moons of Jupiter, okay? And another way that I don't think I even put in here were just solar eclipses. If you see, like we just had recently, if you saw a solar eclipse, you knew, that helped you determine a time length. You knew where it was traveling, and you could be pretty accurate. It could help you if you saw a lunar eclipse, but they aren't so regular to give you any kind of, you can't wait 7 years for another lunar eclipse to come by to tell you where you are in the ocean. But the satellite transits of Jupiter, those little moons of Jupiter go around, there were like 4 transits a day, something like this. Very regular transits. And there were charts of that, and you could look at Jupiter and see the moons of Jupiter and knew enough about it, it could actually give you a pretty good position of this is the time it is in England at this transit, but you're seeing it a different time of day.
So, again, tell us why timekeeping is so important for longitude.
If you know where you're at, the whole thing resolves to the Earth being round and rotating around in 24 hours, right? So that means that every 1/24th of a turn which is 15 degrees, and it's an hour later. We know that we're somewhere around 6 hours behind London. When it's noon in London, it's 6 in the morning here, right? So if you know what time it is in London, if you can tell what time it is in London, timekeeping is an important thing. You can tell what time it is here and compare it to where it is, and that gives you a fairly straightforward development of where you are on the globe, okay? If you can be told that it's noon in London, which any of us can, and you know that it's 10 o'clock, you know that you're further east of London. You're somewhere, maybe Poland or a little bit further east, Ukraine or something like that, okay? Yes?
Wait.
So if it basically comes down to a timing issue, why can't they just use like a series of like the sand clocks, where you have some sand that goes down and then that's like an hour and then you just keep rotating it or and such?
And hourglasses were very critical on boats. They used them, and they corrected them each day. There was people that anytime they had a chance, they re-corrected them, because you get a pretty good evaluation, but humidity can have an impact on the sand. You know, it all had an issue. The wave rocking of the boats can just slow down the sand a little bit. It was not that easy. So some of the problems with the satellite transits of Jupiter were weather issues, taking measurements from a moving platform, really complicated calculations. But one thing that was interesting out of this, you may know that the calculation of the speed of light was determined. People were able to realize that these things weren't happening at the exact same time. They saw that there was a difference in the time it took to transit Jupiter in different places. And they could calculate that, and they came to a calculation that was within something like 5% of being correct by evaluating the differences in the time that it went there. Yeah, I think they saw if you took a calculation in the wintertime when the Earth was on one side of the sun, when it was closer to Jupiter, that was the difference.
Right, it was seasonal.
It was seasonal, and also depending upon where Jupiter is in relation to the Earth, right? And so they could see that this distance the time distance was significant enough that they could see it took a little bit longer for this to occur when the Earth and Jupiter were further away. And so they actually calculated in the 1700s the speed of
I
light.
think it was Romer who did it.
Yeah. 300 kilometers per second, basically. 300,000 kilometers per second, yeah. And then the thing we're looking at, too, is chronometers, right? Very accurate timekeeping devices. How can you do it? If you would take a typical watches in those days, pocket watches and clocks, they had to be corrected all the time. People would take their watch out whenever they heard the noon chimes go at the church or something, which were much more accurate, and they'd readjust every day. People would wind their clock at a right time, wind their watch at a right time, and reset it to a proper time. They were not accurate enough to do this. And accuracy was critical. Temperature and rolling motion on a boat, that could have amazing impacts on what would go on with watches, right, and clocks that were put onto them. So the Longitude Act of 1714 was willing to give 10,000 pounds in British sterling for a method to determine longitude to within 1 degree. Well, 1 degree would give you about 75 miles of accuracy. You'd be about, at the equator, you'd be about within 75 miles of where you thought you were if you could be within 1 degree of accuracy.
Where does a sextant fit into your
Sextants and
Science.
octants and all those were measurements that would allow people to look directly at an object, a celestial object, and it would calculate the angle to the horizon, right? So they were fine instruments that you could, people usually did them, navigators either sat down or laid on the deck, right, and were measuring, and they were telling the point at which in height that an object was.
That would help with north and south.
That would help with latitude. But it also helped somewhat with some of the methods of lunar distance. 15,000 pounds, if you could determine it within 2/3 of a degree, and they were willing to give 20,000 pounds in British sterling for a method to determine longitude to within 1/2 of a degree. 1 degree of longitude spans almost 70 miles at the equator. So you plus or minus 35 degrees, and you'd get 20,000 pounds. And 20,000 pounds, well, 10,000 pounds would equal roughly about $1,250,000 today. So it was a very lucrative thing if you could solve it, but it wasn't an easy thing to solve either. All right. So part of what I'd like to do is then introduce you to the chronometer inventions and developments. John Harrison, very amazing carpenter. His father was a carpenter, and most people went into their dad's businesses. He was a skilled carpenter. He played the viol. He tuned the church bells. He was a choir master in the town near Hull, England, on the eastern side of England. He was about town maybe 5 miles south of Hull. So he was a clockmaker. First known one he made in 1713. It still exists and is made almost entirely of wood. It's a phenomenal thing. The patterns, what he shows, what he knows about grain structure and how to make things so that they lasted. The gearing didn't break off like tiny gears might break off because he used the heartwood of the tree and did it in specific ways. He just showed a phenomenal capacity to work with wood. And he made it before he turned 20. And people those days are saying, young kids nowadays too. He addressed the difference between solar, which is true time, like what a sundial would show you exactly when you're at that lowest point of the shadow, and a clock's mean time. A mean time is artificial, but it's actually more regular. Okay, so he addressed it, and he showed how to correct for that too. He built a tower clock in 1722 that still tells time, and it's been running continuously for over 300 years. Okay? They actually shut it down for some maintenance in 1844 or something like that, and it's been running continually since then too. They shut it down for a week or two. Just phenomenal, phenomenal skills. You can kind of see in the back, on this side is one of his chronometers that ended up going to the West Indies, I think, to measure time there. And on the right, this is a pendulum regulator, and he used this to measure the inaccuracies, to measure how accurate the clocks that he made were. This was a very common, predictable thing that he could use. It was a tool that he was using to make his other clocks. That one couldn't have traveled on a boat or done anything, but it was a very consistent, regular swing of that pendulum. He was doing things that were amazingly anti-friction. He developed ball bearings, first man to develop ball bearings, anti-friction devices, escapements, and different terms that are very important to watchmakers are involved in this. This is the clock. It's a picture today, or recently, that's showing Brocklesby Park. It's a stable and tower. Up there is a clock that he built in here, and it's in a stable. It was on an estate. And here's some of the woodworking that he did, and brass work and so on, that was able to tell time on this thing. So just fantastic when you think of something lasting for over 300 years. He got interested in this longitude problem, and he came up with an idea of how to make a sea clock that could be taken on boats and be used to tell that time difference. If this thing can keep accurate time to within, a few seconds over a course of a trip to the West Indies from London, then you have a very accurate means of telling exactly where you are. So he took about 5 years to build this. He went and he met with people at that were involved with the Longitude Act and so on, that the board that was with that. And he took about 5 years. It weighed 75 pounds and measured 4 feet in each direction. It was originally, all his clocks were inside wooden cases, right? When they brought this down to the boat for him to take it, they had 4 men with big staffs that carried it, and they carried it onto the boat. And this is how it looks today. It's actually been reclaimed. There was a man that reclaimed it right after World War I. The original wood housing is lost. It resides and works today with daily winding in an armored glass box at the National Maritime Museum in Greenwich, England. It was taken for a sea trial to Lisbon in 1736. He was violently seasick the whole time, but the clock worked perfectly. There were things that he should have had some of these, things on his head or something like that to help keep him balanced. But he had plans to improve it, and he never actually pushed for compensation. He never pushed to get this prize. First of all, it was supposed to, the Longitude Act said it had to go to the West Indies, and for some reason they sent it to Lisbon instead, and they weren't putting a lot of emphasis on his work. And he never pushed, well, let's send it to the West Indies and see. But he said he had seen, as he built it, some of the issues, and he thought he's just going to go on to his next clock, which now they call it H2 is his next clock. But you can see the different spring actions in here and all the different things that were meant to keep time perfectly. You can watch videos. If you look at Harrison on videos, you can see some animations of how these clocks work. And these clocks and the 2 others he made after that, H2 and H3, are all running in Greenwich. If you go to London, you can take a boat down to Greenwich. You can go up to the Maritime Museum there, and you can see them running there. And they're all almost like chatting with each other, tick, 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 talking their own language to each other. So this is, if you want to write this down, redfernanimation.com, and you put in the Harrison timekeepers. They show pictures of the actual timepiece, and they show animations like this is showing the things moving and how he controls the movement. Most clocks in those days, if you wound them, as you wound them, they didn't keep time anymore, right? So you lost accuracy anytime you wound a clock. It wasn't operational for that, 15 seconds or whatever you were winding it. So you lost 15 seconds right there. But his were able to continually work no matter whether they were being wound or not. He also is the first person to invent the bimetal strip. If you know the bimetal strip, 2 different types of metals. And a spring out in different temperatures will stretch and change and will release and give effort out at different rates, again, causing inaccuracies. His bimetal strip kind of contained the spring, and as the spring expanded, as it got warm, the bimetal strip would expand because it got warm too, and because there were 2 different kinds, it would bend a certain way, and it would maintain the same timber of the steel that was in the spring. So amazing, amazing things. You see those in thermostats. Not the current thermostats from 20 years ago or so, okay? So he had developed all those kind of concepts. These are pictures of H2 and H3. H2 never went to sea. He took about 2 years to make H2 after he'd taken 5 years to make H1. And H2, he thought he learned so much making H2, he just started making H3 again, making H3. And this had bimetallic strips and caged ball bearings in it and so on. H3 over here is amazing piece of engineering. He spent almost 19 years on H3. And each time, this one never went to sea, so it never got trialed. this one his son took to the West Indies. And I think in the trip there and back, it lost 5 seconds of time. Okay. His big problem was he was competing he was competing with the people that were on the longitude board were also the members of the Royal Society. They were astronomers, and the Royal Astronomer was automatically on the board. And they thought all this was kind of petty stuff, you know. They liked the elegance of the universe, right? So, amazing things in there. So he didn't get recognition for this too much. Then he went on to this one, which is about 5 inches across. His H4 is actually a sea watch. And he gave up some aspects of it. The first 3 never needed lubrication. In 300 years, they hadn't needed lubrication now. This one needs lubrication. And it was more of a commercially usable kind of thing. When they saw what he did on this one, the board said, well, you have to make us 2 more, because we can't take this one out on a sea trip because it's too valuable. So you have to make us 2 more. And by this time, he was in his 60s. He'd spent 45 years making clocks and only getting like little stipends from the government for a while. So this is the external function of it, and that's the internal workings of it. And you can see in the bottom there, it's John Harrison and Sons, and he's got the date that he made it, and so on, 1759, I believe. And it's just the beautiful ornate work on the internals parts of it, and the nice scrolling there, and so on. But they didn't allow this to go to sea either. He had to make 2 more, and they assigned him another guy. He said, I can't make 2 more. He's in his, I think, early 60s or something like that. And they assigned him a guy, and the 2 of them made a watch together, and James Cook took that watch called K1, named after the guy who made it with him. And that was taken by Cook along on his great exploits around Hawaii and so on, Alaska. And he reported how valuable it was. Every once in a while, when they got to a place with a known longitude, they could recalibrate the watch too. You know, when they knew the exact longitude of a certain place, so they recalibrated the watch based on that. But for 5 years, it was used by James Cook through that time, and highly, highly recommended by him. This is more of a, as it sits today, if you get to the museum in Greenwich, you can see that's the internal workings of it, and it's just a masterpiece of just beautiful work. It's sitting on like a crystal or a plastic clear thing, just so you can look at it and see it, but just the workings of it. It's about 5 inches in diameter, something like that, big around. So that's pretty much my talk. I thought maybe there'd be some other questions or thoughts about it, and we'll go on from there.
Who won the prize?
The prize was never actually given out, just like most governments figure out a way to sneak by something. The prize was never actually given out. There were stipends paid against it. They put out somewhere around 100,000 pounds to different people that were doing different things. Some of the royal astronomers got it. The interesting story that I didn't spend much time with was he had rivals and people that didn't like him, and they had positions of power on the board, and the royal astronomer Maskelyne was very much of a rival to him. He actually, because he was on the longitude board, he got a writ that allowed him to take the 3 H1, H2, and H3 away from, confiscate them from Harrison. And in the matter of confiscating them, they were going to trial them and put them through tests and so on, and he put them on like lighted sills of windows where the sun hit it and different things like that. But even in the vast act of just taking the thing away from John Harrison, his workmen dropped H1 and damaged it. You know.
I like using this story, talk about innovation. It's got a lot of messages. One of them is the prize thing is really cool, because if you put up a prize, whole bunches of people spend whole bunches of money doing stuff you could never afford to pay for. There's been at least 2 longitude prizes since. There's one right now running for improving the other thing is this whole point you're making right now about the fact that everybody, once you get a great idea, somebody tries to steal it, and these guys were really good at ripping this dude off. So he really did a lot of good work, but he did it all alone, locked in. You know, he was like the Unabomber. He's off in a corner working on this stupid thing, and his actually did something good. We may have some Unabomber fans here, I don't know. Nevertheless, but those kind of lessons I find to be really important in talking to people about how you actually make this stuff go. And so anytime you're trying to improve anything, I think these things are helpful.
Yeah, I think they talk about, like, what do they call them, incubator zones and things like that, and they try to do that, and it obviously has a value to it. There's also people that find ways to get into an incubator zone and make a lot of money and not do much work, but just kind of baffle people with the bullshit or something like that, and make some money. George?
Yeah, I'm a mechanical engineer by training in nature, and John Harrison is a giant in
Yeah.
mechanical engineering.
Yeah.
And this was a tour de force of clockmaking. I mean, I think you can't emphasize that too much. He is just, in mechanical engineering, he is in the pantheon of one of the greatest.
Like Leonardo and Benjamin Franklin.
Yeah, there were some aspects of him. He was incapable of writing sentences. When he wrote some descriptions of what he did, one was a 26-page run-on sentence that described what he did. So he had a lot of incapability to maybe hearken people to his point of view, and part of that is being an isolationist, working on his own and being afraid of people taking his knowledge and so on too.
And there's many examples, like John Goddard is another one that falls in that category. People don't know much about him because he was a recluse and refused to share his knowledge and his learning until much later.
Right.
That was kind of cottoned onto. But just in general, some comments I might make. We talk about the North Pole and true north. I don't know what that is, frankly. But there's at least four, maybe six definitions of the pole. And a lot of people look at, the North Star, right? Well, you know, Scott didn't put the North Star out there. It does not align with the rotation of the Earth's axis. It looks like it aligns, but it doesn't actually align. And part of my point there is, so we talk about, anchoring to the seafloor, or, and what you're trying to do in general here is you're trying to linearize something that can't be made linear. This is something man just is obsessed about. Putting straight lines on things that can't be done. It's an oblate spheroid.
Right.
It's not a sphere.
Right.
The seafloor moves through plate tectonics.
Right.
The moon has apogee and perigee, and in fact, it's moving way farther from us as we speak. That orbit is not stable. So all of this is dynamic, and to try and corral that into a system of straight lines, as you pointed out, is extremely difficult.
Right.
But obviously, we need to do this for good reasons.
Yeah.
And we do the best we can.
Basically, you're trying to make a model, right? So this is a model, that's a model, this is a model. Even words and speech are a model trying to explain what's there, but it doesn't explain the details, the preciseness, the beauty, the inaccuracies involved in all of that come to fore because of that. So I think you spoke well to that. Yeah, thanks.
That does lead you to the question of usefulness of accuracy. People started asking NASA, do you use Einstein's physics for this? Hell no. We use Newton, and we just keep adjusting as we get there. I mean, this whole idea of getting a perfect place to shoot the perfect place, it's great to keep finding it, but practically speaking, most of this technology we use and stuff like that is, close enough. And don't forget, when we first had GPS, it was already deliberately pushed off to 16, 20 feet, just so you couldn't use it for accuracy, like the Ukrainians are doing so well right now.
There was, when you think of, I agree with the points we're making, and you want to strive for perfection and beauty and accuracy and so on, but when you have 10 men a day dying of scurvy on your boat, you just want to get your boat to harbor, and you want to have a model, a method, a technique, a way of doing that's going to solve the problems that keep your boat floating. But yeah, and that's the balance in science, right? Of solving a problem of today but also realizing that it only is solving a problem. It's not explaining everything in beautiful harmony.
You explained the importance of Greenwich. We now recognize that as zero longitude.
Right.
But going back before the convention, there were many places that claimed to be zero longitude.
Right, right. The Canary Islands was proposed because that was one of the last real things that would be considered in that hemisphere, right? That it would separate the two hemispheres, the eastern and western hemisphere. Why have part of England be in the eastern hemisphere and part be in the western? Paris was a place for scientists, and a lot of people wanted Paris to be. They had it in hundreds of places. Ptolemy was doing work on some of this nature. He figured out the circumference of the Earth to a factor of about 5% accuracy or something like that in, a couple hundred years before the birth of Christ. And in that time, he was in Alexandria, and so Alexandria was the prime meridian at that time.
You have the prime meridian up there, and that's a straight line. So how did they determine the points along the straight line that started the very first straight line from which they established all the rest?
Yeah, that's just the north-south, which you can get from observing the sun and other celestial bodies directly.
I didn't hear exactly what the question was, but
Yeah, how did
thanks
they-
for coming, everyone, but yeah, we'll continue talking. And remember, if you can, sign up for the Science Sunday, Science Slam
Yeah, there's
sign-up
like
sheet.
40 people in
Try
here.
them
There's got to
back.
be at least 10 or 15 good little presentations, a little 5-minute talk, a little demo. If you've got an idea
Okay.
for something you can talk about or demonstrate in 5 or 10 minutes, depending on how many people we have, just let us know. Because 2 weeks from now, it's your Science Sunday.
All right, thanks so much for coming, and be around for talking more.